all the speakers in this symposium are distinctive. Our next speaker, though, has something that no other person on the program has. And that is, he is the only speaker who himself studied under a former Tyndall laureate. Milt Kerker won the Tyndall Award in 1971, and his mentor years ago at Columbia University was Victor Lemaire, who won the award in 1956. So that's a 15-year span, Milt. You learn lots of things from the person you study under. One of Victor Lemaire's big accomplishments, and he was a big man, was his skill at ballroom dancing. I don't know whether he taught you anything about ballroom dancing or not. But you did, in 1971, talk about high-order Tyndall spectra and surface-enhanced Raman scattering. And the title today is Some Optical and Dynamical Properties of Aerosols. Milt Kerker.
If I speak about all the errors you made in that introduction,
Tell me
I'll
about
need some extra time. Well, Howard Reese was a student of Lemaire's, and you got the order mixed. Today's talk is higher order Tyndall spectra and surface enhanced Raman scattering. The Tyndall talk was on aerosols. But I'm glad you brought Victor Lemaire's name up, because this is a subject on which I worked with Victor on my PhD thesis starting in 1987. And surface enhanced Raman scattering is a subject which I've been interested in the last several years, really the last 10 years. But what I want to do is really change the pace a little bit and look at some historical ramifications here, because I've encountered a rather interesting facet that these two seemingly disparate subjects, not really that disparate physically, but do have interesting historical interconnections. And they're each derived really from two separate channels in light scattering theory, which go back quite a ways. The first starts with an interest in the colors of gold and other sols, and it goes back to Michael Faraday. And through him, it became a central problem in colloid chemistry, resulting in the great work of Richard Zsigmondy, and through him, experimental and theoretical work by Gustav Mie, which really has become the definitive theoretical work in light scattering. The second channel is one that goes back to Michael Faraday's assistant and successor at the Royal Institution, John Tyndall, who's interested in the color of the sky, work which was taken up by Lord Rayleigh, who throughout his career worked on light scattering theory and experiments, and interestingly enough, was the first person to prepare sulfur sols which showed higher order Tyndall spectra. And directly from the work of Lord Rayleigh was taken up by others, Keenan Porter, and ultimately by Raman. Raman's first paper was published. First light scattering paper that was published on higher order Tyndall spectra, and ultimately Raman covered virtually all areas of light scattering theory and practice, and discovered the Raman effect. And these two come together in surface enhanced Raman scattering. So what I want to do is trace out these interconnections. If I can have I just have two slides which are rather poor representations of the higher order Tyndall spectra. This is a photograph that was taken in Lemaire's laboratory over 40 years ago, and the colors are not at all, they don't at all resemble the brilliant colors that one sees as one shines a light through a monodispersed colloidal dispersion, in this case sulfur sols, and at different angles one sees different colors. And if I hadn't come on a commuter flight, I would have brought the demonstration along, and you would have seen these absolutely brilliant reds and greens and blues at different angles of observation. That's all for the slide. Thank you. Now, the phenomenon can be understood rather simply. One thinks about light scattering. One has a particle characterized by a certain size, shape, refractive index. One has an incident wave, a scattered wave, and a field inside the particle. This is a problem with electromagnetic theory. Subject to the boundary conditions, one can calculate the electromagnetic fields throughout space. Now, if one does this for a single spherical particle, one gets a radiation pattern, which is traced out here. Imagine that's the particle. Suppose we're in an equatorial plane, and the intensity of the scattered field shows a rather shows a definite lobe structure. The parameter that enters is the ratio of the radius of the particle to the wavelength, and so you'll get a different radiation pattern for red, blue, and green light. There'll be certain angles at which the red light predominates, other angles which the blue light predominates, and as long as the system is monodispersed, so you don't get a mixing of the colors, you'll see this brilliant effect. And one of the things that Lemaire used to brag about, which is quite true, was that you can get the particle size by analyzing this, and if you want to do it by rule of thumb, all you have to do is take the number of times that you see reds in 180 degrees, divide by 10, and that will give you the average size in tens of microns. Now, surface-enhanced Raman scattering was discovered more recently. This was the result of an attempt to see Raman signals from a monolayer on a surface. The first measurements were carried out by Fleischmann, Hendra, and McQuillan in 1974. They used a roughened silver electrode surface, the idea being that if they roughened the surface, they would get a large surface area, they'd get a signal from a larger number of molecules, and hopefully be able to see a Raman signal. They did get the signal, but their explanation was not correct. The correct explanation was provided by Jean-Marie Van Dyne, Crichton, and Albrecht in 1977, who did the experiment more quantitatively and found that the signals that they got were about 1,000,000 times, 10 to the 6 times greater per molecule than one would get from the same number of molecules in solution. And although the surface area is increased somewhat, it might be increased by 20, 25, 50%, in no way could the increased surface area account for the enhancement of the Raman signal. And this set in train a great amount of activity, a great deal of interest, and there were a number of facets that had to be accounted for. First of all, why was it necessary, which it was, to have a rough surface? Secondly, why was it that certain metals, particularly silver, gave an enhancement which was greater than that from a dielectric material, and even silver was greater by far than other noble metals such as copper or gold. And furthermore, it was a resonance effect. That is, the Raman enhancement depended on a particular part of the spectrum in which you looked. And this is not typical of normal Raman scattering, where there's simply, one gets a signal at any frequency, which goes inversely as the fourth power of the wavelength, but is not tuned into any particular part of the spectrum. Well, the way the phenomenon is transferred to a problem in colloid chemistry is depicted here. One can think of the phenomenon as being due to Raman-emitting molecules on a rough, absorbed on a rough silver surface. And one school of thought was that perhaps the curvature of the roughness had something to do with the effect, that it was an electromagnetic effect in which the electrical fields were affected by the actual structure of the surface. And one could conceive then of the rough surface being modeled by an array of spheres on a silver surface, the spheres themselves coated by the Raman molecules. One can carry that one step further and presume that one might get the effect if one had a colloidal distribution of silver spheres immersed in a dielectric medium with the Raman active molecules on the surface. And indeed, Crichton at the University of Kent did some experiments with Faraday sols, which exhibited this phenomenon. This is what got us interested in it. We developed a theory for the phenomenon, which was a straightforward electromagnetic theory, in which again one has a particle, in this case a silver particle, characterized by a shape and a refractive index. One has an incident wave at a pumping frequency. One has a wave inside the particle. One has a scattered wave, just as in ordinary elastic light scattering. But now, in addition, one has a Raman molecule, which will be modeled as a dipole, adsorbed or near the surface. This dipole now feels the electrical field at that particular location on the surface, and that field now pumps the Raman process, and one gets emission of radiation from the dipole at some shifted Raman frequency, in this case shown as omega. One has a second electromagnetic theory boundary value problem, in which one has a dipole sitting on the surface, which now radiates. That radiation penetrates inside the particle. The dipole also is a source which radiates directly to the observer, and in addition, there is a scattered field from that dipole which goes to the observer. One again has three fields, as in the other model. One can solve this as a boundary value problem and calculate the strength of the Raman field at any point in space. And if one does that and takes a small silver particle and calculates the Raman enhancement as a function of incident exciting wavelength, one finds that depending upon the size of the silver particle, one gets tremendous enhancements. For very small particles, a 50 angstrom particle, one gets enhancements of the order of 10 to the 6th. Larger particles, not so great. You might notice that the resonance here occurs precisely at the point that Janusz Fendler showed absorption maxima in his silver particles this morning, and this then can be extended and provide a machinery for calculating the effect. One can do the experiments with small silver particles, and for reasons known only to the Lord himself, who created silver during the first 6 days of creation and gave it these dielectric phenomenal properties. One can do the experiment. In this case, we have a silver sol, which is now illuminated at 1, 2, 3, 4, 5 different frequencies. Now, in this case, we have the 1400 reciprocal centimeter line for citrate adsorbed on the silver. Over here, we have the same experiment with a 1.37 molar sodium citrate solution. The concentration of citrate on the silver colloid is 6.4 times 10 to the minus 6th. And so if one compares the areas under these curves, takes the concentrations into effect, one gets an enhancement of about 4 to 600,000. So that's that phenomenon, as well as the higher order Tyndall spectra. Now, what about the historical sources of these phenomena and the connections about which I've spoken? One goes back to Michael Faraday, who wrote a remarkable paper in 1857, did a whole series of experiments on colloidal gold and other metals. He worked with thin metal films, metal island films, Langmuir-Blodgett built-up films, aerosols, hydrosols, and gels. He worked on all of these different elements, but of course the work that's best known are the beautifully colored gold sols, providing the ruby color that one sees in stained glass windows. And Faraday recognized that the source of the color lie in the colloidal properties of the metal. To quote him, "It's hardly possible to examine a series of ruby glass, ruby membrane, ruby jelly, cold and gelatinous, ruby jelly, warm and fluid, and the ruby fluid, to consider their production, and then to conclude that the cause of their ruby color is not the same in all. Indeed, the various preparations of gold, whether ruby, green, violet, or blue in color, consist of that substance in a metallic divided state." Now, there's all kinds of colloid chemistry in that electrolytic coagulation, all kinds of colloid chemistry in that paper. And that paper provided the research program for much of the colloid chemistry during the next part, the rest of the 19th century and at the turn of the century. In particular, it provided the starting point for the work of Richard Zsigmondy, who worked on stained glass, worked on Faraday gold sols, wrote a book called Colloidal Gold, won the Nobel Prize in 1925. But this was in the mainstream of colloid chemistry at the time, attempts to account for the colors of metal sols and other properties of metal sols, work which had begun by Michael Faraday. Now, Zsigmondy's work was taken up by a German physicist, Gustav Mie, in the first decade of the 20th century. Mie wrote a theoretical paper in which he was able to account for the colors of the gold sols as a purely electromagnetic phenomenon. He showed that the colors depended upon the particle size. The larger they become, the more their color changes towards yellow and red. And in addition, Mie and one of his students published a rather detailed experimental study of these colloidal gold sols. Mie's work entered the mainstream of light scattering theory. It really wasn't the first paper. There were other papers, but Mie's paper has taken over because possibly of its relationship to a practical phenomenon, and light scattering theory from that point on became known as Mie theory, even though he wasn't the first one. But he was the one that applied this to a problem in colloid. Now, going back to the second historical channel that I want to follow, we go back to the Royal Institution again. We go back to the work of John Tyndall. John Tyndall was Rayleigh's assistant, and he succeeded Rayleigh as director of the Royal Institution. Of course, was Faraday's assistant and succeeded Faraday as director of the Royal Institution. Of course, Lord Rayleigh himself was a professor at the Royal Institution for many years. Now, among the contributions of Tyndall was the work that he did on aerosols, preparing aerosols in the laboratory as a result of a serendipitous accident. But this got him interested in the problem of the colors of aerosols and the relationship of the color to the blue of the sky. And in his own words again, in all cases and with all substances, the cloud, the aerosol cloud, formed at the commencement, and this is a photochemical cloud. The cloud formed at the commencement when the precipitated particles are sufficiently fine is blue, and it can be made to display a color rivaling that of the purest Italian sky. If you're very lucky, which I was on only one occasion, you can see a blue Tyndall effect in the dark that is absolutely phenomenally beautiful. In all cases, moreover, this fine blue cloud polarized perfectly the beam which illuminates it, the direction of polarization closing an angle of 90 degrees with the axis of the illuminating beam. I now beg to draw to the attention of the Royal Society to two questions: the blue color of the sky and the polarization of skylight. These questions constitute, in the opinion of our most eminent authorities, the two great standing enigmas of meteorology. It rests with the undulatory theory, the wave theory of light, to explain why. Well, the challenge was taken up by Lord Rayleigh, directly following the work of Tyndall, and in Rayleigh's own words, "It is now, I believe, generally admitted that the light which we receive from the clear blue sky is due in one way or another to small suspended particles," and he later changed that to gas molecules, "which divert light from its regular course. On this point, the experiments of Tyndall with precipitated clouds seems quite decisive." Whenever the particles of the foreign matter are sufficiently fine, the light emitted laterally is blue in color and in a direction perpendicular to that of the incident light is underlined, completely polarized. Now, Rayleigh continued to do light scattering work throughout his career. I think he probably published more on this subject than any other. He wrote his first paper in 1871. He wrote his last paper during his penultimate year in 1918. There's a paper in 1881 which really contains virtually everything that anyone would want to know about light scattering. I can't think of any facet of light scattering theory or practice today which doesn't find some origin in Rayleigh's 1881 paper. Now, included in that paper is a description of the preparation of monodisperse sulfur sols by the acid decomposition of sodium thiosulfate. Now, that's what Rayleigh says. On addition of a small quantity of dilute sulfuric acid, a precipitate of sulfur slowly forms. The experiment is, in fact, much improved by passing the primary light through a colored glass held in the window shutter. Not only is the direction of maximum polarization more definite and the polarization itself more complete, but the observation is easier than with white light by uniformity of the color of the light scattered in various directions. He was seeing these colored effects, but he wasn't interested in them. He was interested in certain polarization effects which Tyndall had pointed out. And the colors interfered with that, so he filtered the stuff out. However, there were others who came along somewhat later, Keenan Porter in particular, who followed this work up and studied these colors and some of the other optical effects of these sulfur sols. And Rayleigh returned to this in 2 additional papers and attempted to account theoretically for the work of Keenan Porter. But he was unsuccessful in doing this and suggested that possibly there was something wrong with this theoretical analysis, possibly he wasn't looking at this in the right way. Now, here's where Raman comes on the scene. Raman had what?
3 more minutes.
3 minutes. Raman was an undergraduate, brilliant physics student. He was frail. His doctors recommended that he not go to Britain and take a PhD, which is what people did in India at the time, because of the British climate. And instead he took a job as an accountant with the finance department in India. And in his spare time, evenings, weekends, he worked at an institution which was modeled on the Royal Institution, doing experiments. Primarily his scientific mentor really was Lord Rayleigh, and he started doing experiments in acoustics. He made a sufficient reputation so that he was appointed eventually professor at the University of Calcutta. And then he started doing light scattering experiments. And the first experiments he did were on these sulfur sols that Rayleigh had worked on and had not succeeded in accounting for them. Well, let me simply say that Raman analyzed the sulfur sols appropriately, did the appropriate theoretical analysis, and was able to account for these colors. This was the first published paper that Raman had. The next dozen years or so, he established a school which covered virtually every aspect of light scattering. He was interested in what we would today call quasi-elastic scattering, and in the process discovered the Raman effect. And so, what I really wanted to do in this talk, dear me, I want to get back to here it is, first slide. What I really wanted to do then is to simply point out these connections, which I find amusing. Of course, you remember, history is a branch of the humanities. Historian does not take facts and simply document them. A historian selects facts, weaves them in such a way as to tell a story which he finds interesting or useful. The important thing in history, of course, being a branch of literature, not a social science, is how the story is told. And what I've done here is I've selectively picked out some facts and tried to show you the connection between the history of the surface-enhanced Raman scattering higher order Tyndall spectra, which I find of some amusement. Thank you very much. And thanks to the